Alright, so Bacha Body, we were doing oxidation and reduction, and in oxidation and reduction, we were trying to find out what are the oxidation numbers, what are the oxidation states, and we had seen that in some places or in some compounds, even if we calculate the oxidation state by using that X thing, we are actually getting a difference. We have seen what is the maximum oxidation state. So let's say we have seen that the maximum oxidation state is equal to valency electrons. And what is the minimum oxidation state? Minimum oxidation state is valency electrons minus 8. Okay. Now in some compounds, what we have seen is that when we are calculating the maximum oxidation state, okay, it is crossing this valency electrons. Okay. When we are taking it as X. For example, in the previous slide, we have seen the example of H2SO5, wherein the valency state, or rather the oxidation state of S was crossing. Okay, so there are three cases which are possible. Okay, there can be three possible relationships between the calculated oxidation state and the maximum oxidation state. These relationships can be used to find the structure of the molecule. We can basically find out the structure of the molecule. Okay, so oxidation state in some compounds containing oxidation state in some oxygen containing compounds. So case 1 we have wherein the calculated oxidation state is greater than the maximum oxidation state. So whatever oxidation state we have calculated, it is greater than the maximum oxidation state. For example, in H2SO5, okay, in this we have, let's say, X here, we have obviously plus 1 here, and we have minus 2 here. So it will be 2 into 1 plus X plus 5 into minus 2, which gives us 0. In that case, it will be 2 plus X minus 10 is equal to 0. That is X minus 8 is equal to 0. So X is how much? Plus 8. Okay. So what is the calculated oxidation state here? Plus 8. But we know that sulfur belongs to the oxygen group, wherein the maximum oxidation state that is possible is only plus 6. So obviously, this is not possible. Hence, we have to do peroxide linkages. Now, what are peroxide linkages? In which oxygen is combining with oxygen. Oxygen is combining with this element as well as it is combining with itself. So, when we have a peroxide linkage like this, here it is not assigned a minus 2 oxidation number. We know here it is assigned a minus 1 oxidation number. And in case it comes in front of sulfur, okay, so here sulfur for this oxygen will get a plus 1 instead of plus 2. Obviously, if oxygen is alone in front of sulfur, we get 2 double bonds, and that gives it a oxidation state of plus 2. However, if one oxygen is there, then it gets a oxidation state of plus 1. So for every covalent bond that we have for an electropositive element, now comparatively sulfur is electropositive, we will get plus 1, and for every covalent bond with an electronegative element, we get a minus 1. Okay, so if the calculated oxidation state is greater than maximum oxidation state, then we will have to go into the structure. We will have to redesign the structure in such a way that obviously there will be peroxide linkages, because of which the oxidation state of oxygen will go less. Okay, then we have calculated oxidation state is equal to maximum oxidation state, which is absolutely fine. Okay, we will leave it the way it is. Here we have oxidation state lesser than the maximum oxidation state. If this is there, then obviously the compound can go into oxidation as well as reduction. It can afford both ways. It can afford oxidation, it can afford reduction as well. So these were certain cases that we had considered in the previous thing. We will go further deeper this time. Okay, so let's say in case 1, when the oxidation state, the calculated oxidation state is more than the maximum oxidation state that can be supported by the element. The calculated oxidation state is more than the maximum oxidation state. Here there will be peroxide linkages. Very important, people, please have it noted down. So here, if we have the calculated oxidation state more than the maximum oxidation state, here if we have the calculated oxidation state more than the maximum oxidation state, there will be peroxide linkages. Peroxide linkages are linkages like this. Okay, peroxide linkages. So it will be combining with the element. It will be combining with the element, but it will be combining with oxygen. So with peroxide linkages, for oxygen we will have an oxidation state of -1 instead of -2, and the element which comes in front of oxygen obviously gets +1 instead of +2. Okay, so then we have calculated oxidation state is equal to maximum oxidation state. This is basically oxy linkages, which is normal, which is basically normal. And then we have calculated oxidation state lesser than the maximum oxidation state. This is element to element linkages. Okay, okay. Just one moment here. So in this chapter, we will be taking only case 1 in detail. The other 2 we'll learn in inorganic chemistry. There's nothing to learn in the other 2. Obviously, we will have here both oxidation and reduction can take place. Okay. Now let's move into this one. Okay. Calculated oxidation state when it is greater than the maximum oxidation state. Okay. Let's take an example of peroxymonosulfuric acid. So this is peroxymonosulfuric acid. Okay. The reason why the name peroxy is given is because we have peroxy linkages. Okay, peroxide. So oxygen here behaves like a peroxide. Now let's take this one. Okay, okay. So here we have H2SO5. So which means what? If I take this as X, if I take this as +1 and this as -2, so obviously here we will have 2 into +1 plus X plus 5 into -2. That gives you how much? 0. So that will be 2 plus X minus 10, that gives you 0. So X minus 8 is equal to 0. X is equal to +8, which is not possible for sulfur because sulfur has a maximum oxidation state of +6. So obviously it is crossing that maximum oxidation state. Okay, it is crossing that maximum oxidation state. So it is not possible. Maximum oxidation state of sulfur is +6. Hence a peroxy linkage. There will be a peroxy linkage which will be present in peroxysulfuric acid. Peroxymonosulfuric acid, there will be a peroxy linkage. From the structure, the number of covalent bonds between S and O atoms. Now let's look at this. This is an S atom. Obviously we have an oxygen. So for this oxygen which is having a double covalent bond associated with sulfur, it will be -2. This will be -2. Okay, this will be how much? This will be -2, which is basically with H. Okay, now out of this, because of one covalent bond, sulfur is going to get, so this is +2. This is going to give sulfur an oxidation state of +2. For these two covalent bonds, sulfur is going to get a +2 oxidation state, and obviously for these two covalent bonds, again sulfur is going to get +2 oxidation state. One bond, so one covalent bond for which sulfur gets a oxidation state of +1, and here again one covalent bond for which sulfur gets a oxidation state of +1. Now sulfur will have +2, +2, +1, +1, which is +6, which is absolutely fine because that's the maximum oxidation state of sulfur. Now let's look at this. Here it is oxygen. Here it is oxygen. Look at these two oxygens. This is basically a peroxy linkage, or we can say this is basically the peroxy linkage. Here, due to this peroxy linkage, what is happening is oxygen is acquiring an oxidation state of -1. Obviously here it will be +1. So this is the structure of peroxymonosulfuric acid. Okay, so this is what will happen. So from the structure, the number of covalent bonds between sulfur and O atoms is obviously 1 + 2 + 1 + 1. So that gives the required oxidation state to sulfur, which is +6. Okay, so please pay attention whenever you have a case in which your elemental oxidation state is coming out to be more. The calculated oxidation state by putting an X is coming out to be more than the maximum oxidation state which is permissible. You will have to go deep into the structure and you will have to identify peroxy linkages. These peroxy linkages are going to reduce the bonding that is happening between oxygen and the element, because of which the element is going to get down on its oxidation number. We have to have the oxidation number as the maximum oxidation number, not greater than that, because that is not possible. Okay. All right. Let's move on to CrO5. Let's look at CrO5. Okay. We know that the electronic configuration of chromium is argon 3d5 4s1. So how many electrons do we have in the outermost orbit? We have 6. Okay, so here we have 3D. This is basically argon, 3d5 4s1. So the number of electrons in the outermost orbit of chromium we know is 6. Okay, so chromium, the maximum oxidation state of chromium would be +6. Okay, now let's look at CrO5. CrO5, which means here we have -2, here we have x. X plus 5 into -2 gives you 0. X minus 10 gives you 0. So x becomes how much? +10. Obviously, the calculated oxidation state for chromium comes out to be +10. However, the maximum oxidation state that is possible here is +6. So would this be possible? Obviously not possible. So we will have to go deep into the structure of chromium. How do we find out the structure of chromium? Now let's say this is chromium. Okay, with one oxygen, it has got 5 oxygens to associate with. So let's say with one oxygen it forms a double bond, which is basically required for oxygen. Let's forget about chromium. Oxygen will require 2 covalent bonds to complete its octet. That's for sure. Okay, so let's say for this, the chromium atom will get how much? This will get +2. Here it is -2. Now, how much scope is there for chromium? It can have 4 more covalent bonds. It can adjust 4 more, and there are 4 more leftover oxygen atoms. Now, obviously, one oxygen is here, one oxygen is here, one oxygen is here, and one oxygen is here. That pretty much settles down for chromium, because for every single covalent bond, an electropositive element is going to get +1. So this will be +2 here, 3, 4, 5, 6. So the matter of chromium is sorted out. Now we will have to look at this oxygen. Oxygen's octet is not getting complete with a single covalent bond. So what will it form? It will form peroxy linkages. These are basically peroxy linkages. This is how the chromate ion will look like. Okay, this is how the oxidation state of chromium in CrO5. This is how it will look like. So hence a peroxy linkage will be present in CrO5. Actual oxidation state. Here the actual oxidation state is the maximum oxidation state, which is +6. Okay, so this is how we will have to go deep into elements which are crossing their oxidation, maximum oxidation state, which is permissible in a particular element, in a particular compound. Let's talk about peroxy disulfuric acid. Let's talk about peroxy disulfuric acid. So if you see here again, if we calculate the oxidation state of sulfur, here we have 2 into +1, 2x, plus again 8 into -2 is 0. So this will be 2 plus 2x minus 16 is equal to 0. 2 minus 16 gives you -14. You take the -14 here, it becomes +14. 2x is equal to +14, so x will be +7, which is again not possible because the maximum oxidation state of sulfur which is possible is only +6. So let's look at this. The calculated oxidation state again here goes to +6. So calculated oxidation state is more than the maximum oxidation state which is possible. Hence a peroxide linkage will be formed. So how do we calculate this peroxy linkage? Number of covalent bonds between sulfur and oxygen atoms has to be. So now let's look at this. Let's look at the structure of H2S2O8. H2S2O8. So peroxy disulfuric acid, we have seen the case of peroxy monosulfuric acid. There also oxygen's sulfur's maximum oxidation state was crossing +6. Here also sulfur's oxidation state is crossing +6. Okay, so here we have 2 sulfurs to adjust. Where we have 2 sulfurs to adjust, and how many oxygens do we have? 8. Okay, so let's say for both the sulfurs, if we take 2 oxygens normally with double covalent bonds, in this case the octet for oxygen is getting complete, the octet for oxygen is also getting complete. This case also both the oxygens, their octets are getting complete. So whenever their octets are getting complete, in normal scenarios, oxygen will have an oxidation state of -2. So this will have -2, this will have -2, which will eventually give sulfur an oxidation state of +4. Here also it is getting +4. How much of scope does sulfur have now? 2 more covalent bonds with oxygen. So let's take this. So 1 covalent bond with oxygen, okay, and obviously oxygen gets 1 covalent bond with hydrogen. So oxygen's oxidation state here remains -2 because its requirement of octet is getting fulfilled by sharing of electrons with both hydrogen and sulfur. Okay, so because of which this will be, now 1 single covalent bond gives sulfur an oxidation state of how much? +1. So it was already down with +2, +2, +4, +1, that is +5. How much scope does sulfur have now? +1. So let's look at this. So here we have 1 oxygen. Okay, now comes the peroxy linkage. So how many oxygens are we? Same here, one oxygen we will adjust here, which will be in combination with hydrogen, normal oxygen which will have how much? +2 as the oxidation state, because its octet is getting filled by electron sharing between hydrogen and sulfur. Okay, so here with single covalent bond, sulfur gets an oxidation state of +1. So both the sulfurs have now an oxidation state of +5. So they have a scope of 1 more. What 1 more, and with 2 oxygen atoms to adjust. Understand this equation. Sulfur now has a scope of adjusting an oxidation state of +1, which means that with what? So how many oxygens are we left with? 2 here gone, 2 here oxygens are gone, 1 here, 1 here. So how many oxygens total we had? 8, out of which 1, 2, 3, 4, 5, 6. 6 are already gone. So 2 are left. So with 2 oxygens, we have to provide both the sulfurs an oxidation state of just 1. So we will first place these 2 oxygens here. So the moment we place an oxy linkage between them, their oxidation state changes to +1. So when it changes, -1, and when sulfur combines with it, obviously it will get a oxidation state. So here the oxygens are combining with a single bond, which basically fulfills their octet requirement, gives an oxidation state of -1, and sulfur accordingly gets an oxidation state of +6. This sulfur also gets an oxidation state of +6. That's how we will basically look into it. Okay, so this is the oxidation state of sulfur. Now we have a peroxy disulfuric acid. Peroxy diphosphoric acid. So here in phosphorus, let's look at this. Phosphorus, calculated oxidation state of phosphorus will be how much? 4 into +1. 4 into +1 for hydrogen. We have phosphorus 2 into x plus 8 into -2, that is 0. So here 4 plus 2x minus 16 is equal to 0, gives x is equal to +6. Obviously this is not possible. Maximum oxidation state of phosphorus here is how much? +5. Okay, so calculated oxidation state again becomes more than the maximum oxidation state. So again we have to find out peroxy linkages out here. Okay, so hence a peroxy linkage will be present in peroxy diphosphoric acid. So what is the peroxy linkage? Now understand, phosphorus here, how many phosphoruses are there? 2 phosphoruses are there. So we place these 2 phosphoruses here. What is the scope out for phosphorus? +5, which means that we have a total of how many oxygens out here? The total of oxygens out here is 8. Okay, so if we happen to adjust one oxygen with a double bond normally, so oxygen's octet is complete, and because of this phosphorus gets an oxidation state of +2. Phosphorus, this phosphorus as well as this phosphorus gets an oxidation state of +2. So what is the scope now? +3. Okay, because maximum oxidation state of phosphorus is +5. So it has already been adjusted with +2. Okay, now let's look at it. If we adjust one oxygen here normally with one hydrogen, one oxygen with one hydrogen. So obviously here the oxygen's octet is complete by sharing of electrons in a covalent bond with hydrogen as well as phosphorus, Because of a single covalent bond between oxygen and phosphorus, phosphorus gets an oxidation state increment of +1. It was already there with +2 and then again +1, +2 and then again. So both the phosphoruses have now acquired an oxidation state of +3. How much is the scope now? +2. So let's look at it. Here +2, again we have one oxygen with one hydrogen. So again it gets +1, so +4. Again it gets +1, so +4. Now it is remaining with, so all the hydrogens have been used up. We don't have any scope of hydrogen now. Only 2 oxygens are remaining, and the oxidation state that could be adjusted for phosphorus is just 1. So what do? We place these 2 oxygens in between. We place a single bond with them, and obviously phosphorus will have +1 because of this. So since this is a peroxy linkage, your oxidation state, or rather a single bond, this will give +1. So oxidation state of phosphorus is now +5 for both of them, and here in between we have a peroxy linkage. That's how we are going to adjust the peroxy linkages. Okay, so we have here K3CrO8. Let's look at this, people. K3CrO8. K3 is basically potassium tetraperoxychromate. tetraperoxochromate. So this is potassium tetraperoxochromate, calculated oxidation state of chromium. So let's look at chromium. Here we have potassium here. This is basically potassium, and here we have chromium. Okay. So calculated oxidation state of chromium will be how much? So if you see, potassium has an oxidation state of +1. So this will be 3 into +1 plus x plus 8 into -2, that gives 0. That gives basically 0. Okay. So now 3 into +1 plus x minus, so if you look into this, x is equal to +13, which obviously is not possible because chromium again has an oxidation state of +6. Okay. So chromium has an oxidation, the number of electrons which are, or rather the valence electrons present in chromium ion is 6. So this gives chromium an oxidation state of +6. Okay, let's look into this. So maximum oxidation state of chromium here is +6. Calculated oxidation state obviously is greater than the maximum oxidation state. Okay, hence a peroxy linkage will be present in. Okay, so now let's look at it. So chromium here is present. Chromium has got 5 oxygens. So 5 oxygens are there for chromium. So here we have chromium, 5 oxygens, 1, 2, 3, 4, 5. Obviously all of them are giving a total oxidation state of +6 to chromium. So they get a total oxidation state of, sorry, +5. So it gives a total oxidation state of +5. Now how many oxygens are we left with? We are left with 3 oxygens. So 1, 2, 3, 4, 5. Now in this 4, 5, obviously this oxygen will have 1 oxygen here. This oxygen will have 1 oxygen here. This oxygen will have 1 oxygen here. This oxygen will have 1 oxygen here, and so on and so forth. This will be -1. This will be -1, and all these will be -1. Okay. So this is going to be peroxy linkage of potassium tetraperoxochromate. This will be peroxy linkage of potassium tetraperoxochromate. So here we have 3 potassiums. So here 1 oxygen attaches with 1 potassium, which gives it an oxidation state of -1. Again, this will be -1, this will be -1. Okay. So here potassium, this will be basically how much? 1, 2, 3, 4, 5. That will be +5. Okay. So that pretty much solves it. Okay, so let's look at this. What is in acidic medium H2O2 changes Cr2O7 2- to CrO5, which has 2 oxygen bonds. What is the oxidation state of chromium in CrO5? So CrO5 consists of a peroxy linkage, that is OO. For a peroxy linkage, the oxidation state of an oxygen atom is -1. Something is happening. Just one moment, people.